Okay, hello class. We are in book 3.5, chapter 2, and this is where things get really interesting. We're going to start looking at nonlinear space curves, and we'll do all sorts of computations associated with those. And so the first thing, though, in this video, we want to make sure we have a recognize nonlinearity of space curves, R of t. Second thing we want to do is make sure we can visualize some of the more basic ones, and then third thing, resort to some tech tools for the more complicated ones. So suppose we have this. What type of vector function is this? Is it a plane curve or a space curve? Plane curve because it lives in a plane, the R2. If you have a third component, you're a space curve. So we're going to start off easy with just an R2 plane curve here. And we're going to look at this. Let's make a domain for t. Let's just say -2 to 2. So we're just looking at a section of that. And again, you should be able to immediately recognize that this is going to be a nonlinear plane curve. And some of the advantages we talked about in chapter 2 of representing this in a vector function rather than y as a function of x, an explicit R2 function, which you've learned how to do in the past. The advantages here is we talked about you can have orientation along this curve, whereas here I can just write something like this, and I don't know which direction I'm traveling along that. Here I can have a direction of motion, so an orientation, and I can also have a speed. And again, you should be able to immediately recognize nonlinearity because of the cube, but same things that made nonlinearities over here, make them here. If any component, at least one component has a nonlinearity, the whole vector function is nonlinear. So cubes, polynomials, sines, trig functions, e's, ln's, all the same things that you had over here make something nonlinear. So that's the first thing, that's easy to do to recognize. The second thing, we want to get a general sense of what the shapes of these look like. And just like you did over here, you could plot points, and so we've done that also in chapter 1, but let's just to show that we can also, again, this is your x of t function, your y of t function, and in general, we'd have a z of t if we were in R3. So we can put in values for t that then affect the x and the y. So then we have a point that we can plot for different t's. Now our t's range from -2 to 2, so we can pick some points in there. Maybe it's just some nice integers just to keep it simple. But we kind of know it's going to have the shape of a cubic, but maybe not the cubic this way. It might be laying on its side, right? Because the x and y are flipped. So when t is -2, then we'll have -8 in the x component and -2 here. So we can just fill out the last column. Is easy. That's just copying the first column. And then we have to do some cubes here. So that will be -1, 0, 1, 8. Now we have enough that we can plot. Again, we kind of have a sense of what it looks like. So we're just going to plot some points. It's a plane curve, lives in the xy plane. So we have a point -8 along the x and -2 along the y. So one point here, -1 along the x, -1 along the y, 0, 0, 1, 1, and all the way out here. So we have this cubic in this direction. This is our function r of t equals t cubed t. But we put a direction of motion. So we go from the -2s were over here. This was when t was -2. This middle one is when t is 0, and this is t equals 2. So the direction of travel is that way. You can put a couple arrows if you like. Okay, so no problem. We can plot the easy ones. R2s that are easy, even some R3s. So maybe let's look at another one. Let's do an R3 space curve. Let's try t squared, t cubed. R3, we have 3 components now. let's keep the same domain just to keep it simple. So again, you could plot points, but maybe one way of thinking about this too is to say, what if this third component wasn't here? This is a parabola facing up in the xy plane. So if we were just looking at the first two components, we have this. This would be r of t equals t squared. And you go from -2 to 2. And then, so now if you go into your R3, you can imagine that this is the trace of it down in the xy plane. And what is happening now when you add that third component is, so if you were looking directly over top of it, you would see it's sort of the shadow that it would make in the xy plane would be this parabola. But what's going to happen is now the z values are going to come up because of the t cubed for positive when you're above the xy plane. And when you're exactly in the xy plane, we'll be right there at that point. And then when you're below the xy plane, we'll have negative z values, so we'll go below. And so it actually makes something that's called a twisted cubic. And maybe you see it in your desktop or corner coordinate system. Maybe you see it in front of you using your book and think about what it would look like. That might be a good exercise to think about. But we're also going to jump to a tech tool to show you how to plot these and use some of the features of the tech tool. And it's just an extension of stuff we've already done in chapter 1. So we're going to go to Calc Plot 3D. Okay, we're going to turn that preset one off or get rid of it with the X. We will select to add a space curve, R of t. Again, if we just wanted to that first one we did, which was t cubed, t had no z component, it was a plane curve. We went from -2 to 2. Maybe we'll put a couple orientation arrows, restricted to 2D, use a constant primary color. Okay, so that's the first one that we graphed. And we can zoom out a bit. And we can see that goes from -8 to 8 in the x directions. And initial point, this one over here is t equals -2, t equals 1 was here, 0, 1, 2. So you can see by the, not just the orientation, but you can tell a little bit about the speed. So in the 1 second, or if those are the time units from t equals -2 to t equals -1, it travels that distance. And then it sort of slows down. It only covers this much from another 1 unit in the time from -1, t equals -1, t equals 0. Slows down, just keeps that same rate, and then really accelerates here. Okay, so that's how we do a R2 plane curve, but ours now is a R3, the twisted cubic, t squared, t cubed, from -2 to 2. Don't restrict it. Make sure you hit enter to change it. Okay, and this one, again, you can kind of see that once we're below the xy plane, we start getting negative z values. That makes sense. We're above the xy plane, we have the positive ones. If we look directly, it's got that sort of looks like a loop-de-loop there, but really that's just when we look directly overhead, we see that parabola shape that we had expected from the first two components. And then you add the third one there. It gives our orientation. And I don't know if we talked about this yet, but you can also animate this thing as it goes over its range. And yeah, so it's showing from t equals all the way here at the beginning from -2. It's showing the vector represented by that space curve r of t at t -2, r of -2, plugging in -2 in each of the components here. It's showing that that's actually a vector, which can also be thought of as the terminal point of the vector. And it's going to trace that over the red space curve as t goes over its domain from -2 to 2. And let's see, let's check the settings. We can change some things here when we're doing that animation. We'll get to these acceleration vectors and velocity vectors later. Trace vector, maybe let's just show the trace point. Keep that a little bit simpler. And there goes that little black point. Again, watch, you can see the speed as well, animating as it goes through its domain. Okay, so next thing, last piece of the puzzle here, is being able to recognize nonlinearity, plot some basic ones by hand, use a tech tool for the more complicated ones, but also recognizing the general shape of some of these. And we had a hunch for this one, but you're going to do some really interesting activities here in the beginning of chapter 2 to get a sense of what a space curve might look like. And so maybe let's take one. These are your matching activities. You're going to do plane curve matching, a couple space curve matching. And there's some really interesting ones here. So let me just put one of these up. You're going to be able to get a sense of what these look like just by looking at the equation. You don't necessarily need a tech tool. You can always check your ideas with the tech tool. But let's see. Let's look at this one. RT is 4 cosine t, 4 sine t, t, 4 t between minus 6 pi and positive 6 pi. Okay. And this one is going to be something called a helix. You're going to be pretty familiar with these, and especially after you finish these activities. But one thing you can notice, what makes it a helix. So let's ignore this part for a minute, take it down a dimension to a simpler space in R2, and just look at if we did x of t is the first component plus y of t. So what if we did this? Just look at what that is. Well, that would be 4 cosine t squared plus 4 sine t squared, which is 16 cosine squared t plus 16 sine squared t. Pull out the 16 cosine squared t plus sine squared t, which that is 1, so that's 16. So really we have x squared plus y squared equals 16, which is what? From R2, back over here, we would have said, okay, that's a circle with a radius of 4. A familiar surface or a familiar curve that you remember from R2. And what that means is that if you didn't have this third component, you'd be running around on a circle with a certain orientation as t ranges over its domain. Maybe you're making several passes, I think 6 in this case, and maybe in this direction, you have to figure out that to do these activities. And so what's going to happen when we add this third component? So there's really now a z-axis coming out from the board. So rather than just tracing over that in the xy plane, we're actually going to be wrapping around. In R3, this is actually a vertical cylinder. So that vertical cylinder is coming out. And what's happening now is this circle, you're tracing around this, snaking around this vertical cylinder, which is coming out from the board. Or if we set it up, just imagine a soda can and you're running around, but vertically rising as you go around that can. And that creates a helix. Again, you're going to get used to those. You'll see several of them, but here's several different helixes, and it just depends whether they're vertical or laying on their side, or whether they're wrapped around instead of a cylinder, possibly a cone. Or another great example of a helix, something I love about these coils is, right, our coil-bound books are a great example of a helix. Okay, so those are the main ideas in the first set of pages in this chapter, and then we're going to move on with the next video to derivatives.